In this video, we will take a closer look at the atomic mass, specifically how the atomic mass is determined using isotopic data. The atomic mass appears on most periodic tables as a decimal number. Watching this video is one step towards meeting the learning objective of being able to compute the atomic mass from isotopic data using the relative natural abundance and mass numbers of the isotopes. The atomic mass is basically a weighted average mass of all naturally occurring isotopes for elements on the periodic table. It is also called the atomic weight or the standard atomic weight, and is often, though not always, directly under the element symbol on the periodic table. To begin, we will start with the example of neon. Neon has an atomic number of 10, shown here, which is also the number of protons it has and the number of electrons in a neutral atom. The atomic weight is then given as 20.18. How do we arrive at that number? That's what we're going to look at in the next few slides. In order to compute the atomic mass, we need to know a couple key pieces of information. First, we need the naturally occurring isotopes, which are neon 20, 21, and 22, and their natural abundances. The natural abundance is roughly constant for each isotope in naturally occurring samples of that element. For neon 20, the natural abundance is 90.48%. For neon 21, it is 0.27%. And for neon 22, it is 9.25%. We also need to know the mass of each isotope. Since most familiar units are far too large, we often use atomic mass units when discussing the mass of a single atom. 1 AMU is approximately equal to the mass of a proton or neutron, and is much greater than the mass of an electron. For each of the neon isotopes, we can determine their masses as 19.99, 20.99, and 21.99 AMU for neon 20, 21, and 22, respectively. We can then use these values to compute a weighted average of the isotope mass by multiplying a fraction of each isotope by its mass. To get the fraction of each isotope, we take the percentage and divide by 100, and then multiply by that isotope mass, and sum those together, and when we do that, we find we get 20.18 AMU, which is exactly what's shown on the periodic table. In general, the atomic mass can be written out as a sum over each isotope. Here's the formula written out with sum notation. In the sum notation, we sum over all isotopes where we're just multiplying the fraction and the mass of those together. I could also expand that sum out into individual isotopes, and this is written with ... to indicate that that's for as many isotopes as there are naturally occurring. Before we discuss how we determine natural abundances and masses, I want to make a quick comment about the units used. So far, we've been using AMU for individual atoms, and we've said that 1 AMU is approximately the mass of a proton or neutron. However, we find that 1 AMU is also equal to 1.66 times 10 to the negative 27 kilograms, and we can use this value as a conversion factor to convert from AMU to kilograms. And then we could go from kilograms to grams, and we could count by moles. Don't worry right now if you don't see why we would want to do this, but trust me that it's useful. Now, if we start with the mass of neon, which was 20.18 AMU, and do these conversions, so the first conversion here is going from AMU to kilograms, and then the second one is going from kilograms to grams. The one we're going from is always in the denominator. The unit we're going to is always in the numerator. And then I'm also multiplying by Avogadro's number. So it has an implicit unit of atoms per mole. So when I multiply this out, you'll see that I start with 20.18 AMU, and I end with exactly 20.18 grams per mole. So this means that the atomic mass that you see on the periodic table can either be read as AMU when talking about a single atom, or with units of grams per mole when discussing a mole of atoms. So just be aware that this number can be read using two separate units. elements. Experimentally, the atomic mass is determined using a technique called mass spectrometry. Mass spectrometry can detect the individual masses and their relative abundance and produces this information as a spectrum, such as what's shown here. Actually, we'll see on the next slide that it detects a mass-to-charge ratio and how frequently that particular ratio is found at the detector. So in mass spectrometry, a sample atom or molecule is first ionized by interaction with a beam of electrons. This process removes an electron and results in a positively charged cation. Most often this has a +1 charge, and so we can assume that is the case for the purposes of this class. The charged ions are then accelerated through some electrically charged plates and deflected using a magnet so that the ions separate based on their mass. These different particles are then detected, and the number of each mass that hits the detector is counted. This results in a spectrum, such as what is shown in the previous slide. Now let's look at a different example, which is computing the atomic mass of chlorine from its mass spectrometry data. From the mass spectrometer, we find there are two isotopes of chlorine, chlorine 35 and chlorine 37. We also find that 76% of the particles deflected are chlorine 35 and 24% are chlorine 37. More significant figures are also given in the write-up of this problem, and it's important to always use the values you're given. So we need to calculate the weighted average using these values, which we can do by converting first the fraction to decimal form. So again, we take the 75.77 and divide by 100 to get 0.7577, and 24.23 divided by 100 gives us 0.2423. So that's our fraction, and then we multiply that by each of the masses, and finally we sum those together to get the total atomic mass, which is 35.45. And when we compare that to what's on the periodic table, we find that it's exactly the same value. Now it's your turn. Take a minute to estimate the atomic mass of silver based on this given mass spectrum. Although the highly accurate masses and intensities cannot be determined from this chart and have not been given, you should be able to make a decent estimate, and you can compare your result to the value that is found on any periodic table. Thanks for watching, and enjoy your practice.